So we continue our afternoon session. It's a great pleasure to introduce live from Leipzig, Anna Wienhard, a great mathematician, a fantastic tennis player, partner of mine for more than 20 years, who is going to tell us about positivity and higher Teichmüller spaces. Anna?
Yes, so thank you very much. And I would like to thank you for the organizers for the invitation. So it's a great honor to be able to speak here. And it's really a pity. And I'm really sorry that I cannot be there in person. So I unfortunately miss all the fun. So I would like to start with mentioning the paper of Nigel, which probably had the biggest influence on me, his paper on Lie groups and Teichmüller space in the Journal of Topology from 1992. This was actually not the first paper I read. I mean, before I read this paper, and I didn't read it in 92, but later, I had looked at his, when he introduced generalized geometry, a little bit at that, and heard Nigel talk about other things at the Arbeitsgemeinschaft in Bonn when I was a student. But it's really, I would say, this paper which had the biggest influence on my mathematical endeavors. And so what happens in this paper? So let me pick out a few things. So in this paper, Nigel Hitchin introduced what is nowadays called the Hitchin component. So a connected component of the space of representations of the fundamental group of a surface into a split real Lie group G, which astonishingly is homeomorphic to a vector space of the dimension you would expect, namely 2G minus 2, where G is the genus of the surface, times the dimension of the group. And so so really this property is really astonishing. It's not so difficult to define the Hitchin component because it's a connected component. So to define it, I essentially have to give you one representation. And to give you one representation, you use a trick if you want to map the fundamental group of a closed topological surface of genus bigger or equal than 2 into any Lie group G. You use SA2R representations, because we all know that we can represent the fundamental group of a closed surface of negative Euler characteristic in the isometry group of the hyperbolic 2 space. So in PSA2R, we can also lift it to SA2R. And then whenever we find an SA2R in our Lie group G, we can pre-compose it with a representation of the fundamental group of the surface, which is discrete and injective here, and get one representation from the fundamental group of the surface into G. In order to land in the Hitchin component, you have to pick a special SA2, and you need to pick the SA2, so the SA2 subgroup, which comes from a three-dimensional principal subalgebra in the Lie algebra of G. And these three-dimensional principal subalgebras exist for all split real Lie groups. And so once you have this, you can give this one specific representation and then say, well, you look at the connected component of this representation. But usually, if you just do this with any other embedding of SA2R, you get something which might not be smooth at all, has singularities, might have non-trivial topology. So it's really quite remarkable that here you get this connected component, which is homeomorphic to vector space. And so I mean, this gives you the definition of the Hitchin component, but of course this is not, it doesn't give you at all a mean to prove that. And how do you actually, or how did Nigel actually prove that? For this, you go to the theory of Higgs bundles, and you consider the complexification GC of your group G. You pick a Riemann surface structure on your surface S, and instead of looking at the space of representation of the fundamental group, you look at the moduli space of Higgs bundles on this Riemann surface sigma into so with respect to this complex group. And then you have, and this is something which Nigel had defined earlier already, the Hitchin map, which sends any Higgs bundle by taking the Higgs field to the sum of holomorphic differentials. And then to get the Hitchin component, which, I mean, Nigel actually never called the Hitchin component, but the Teichmüller component, he constructs the Hitchin section, so a section to this map, and then shows that actually the image of this section, first of all, lies in the real points, give you representation in the real group, not only in the complex group, and it gives you an open and closed subset. And so this way you get this very nice feature that this connected component is homomorphic to a vector space, but you don't get much geometric information. And so at that point, I was not studying Higgs bundles at all, but I was interested, and I got interested in Nigel's paper because of results of Choi and Goldman around the same time and the paper appeared, and Labourie and Fock and Goncharoff around 2002, where they proved that actually these representations in the Hitchin component, they don't just have, the Hitchin component doesn't only have a nice property as a subset or as a connected component, but each individual point in the Hitchin component has nice properties, namely it's a representation which is injective, so faithful, and has discrete image. And there are further properties you can establish, but I don't want to mention them here. And so this is really why I got interested in that, because at the same time with Mark Burger and Alessandro Iozzi, we were investigating completely different representations of fundamental groups of surfaces into essentially completely different groups, namely so-called maximal representations. And I don't want to give you the precise definition, but what so the space of maximal representations also gives you a union of connected components, actually. And what we proved was that any representation in the space of maximal representations is also discrete and faithful representation of the fundamental group of your surface. So there is a very similar result for maximal representations and for representations in the Hitchin component. And we will see that there are also many differences, but this caught my interest, and that's why I actually started looking at Nigel's paper. And as several of you in the audience remember also, we started having this discussion with Steve and Oscar, somehow getting, for me, trying to get to understand better and knowing more about Higgs bundles. So after this, somehow having these very similar results by Labourie and Fock and Goncharoff for the Hitchin component and our results for the space of maximal representations, I got interested in understanding these spaces better. And before I go and say a little bit more about that, so let's for a moment put both of these together, the Hitchin component and these spaces of maximal representations, and call them higher Teichmüller spaces. And for me, as a definition, at this point, I would like to take the following definition. So if I have a closed surface and I look at its fundamental group, and I look at the representations of the fundamental group into G, up to conjugation by G, I call something a higher Teichmüller space if it's a connected component or a union of connected components which exists entirely of discrete and faithful representations. And so these results give you two examples of such phenomena. And so after these results, I wanted to understand these higher Teichmüller spaces better. And the first, one of the first things I got interested in is actually question which is raised in Nigel's paper. So basically it says, okay, so you have this Teichmüller component and you know it's homomorphic to a vector space, but this shouldn't happen without any reason. So it was his question whether the Hitchin component really parameterizes some geometric structures. And in one case, this was confirmed directly by Choi and Goldman in the case of SL3R, where they showed the Hitchin component parameterize a convex real projective structure on the surface. But for other cases, this was not clear. And the results by Labouille and Fock and Goncharov didn't give explicit geometric structures, but again, showed that there are a lot of properties like discreteness and faithfulness that you should expect geometric structures to be parameterized by these special components. And so I would like to not discuss this in detail, but I mentioned one theorem which puts together work which we did with Olivier Guichard in 2008 and 2012, and then very recent work with Alessandrini, Maloni, and Tolosan, which you can summarize in the following statement, that all Hitchin components parameterize geometric structures on manifolds which are compact fiber bundles over your surface S. And which compact fiber bundle you get is actually not unique. So there are many different choices you can make, but there are many constructions where you get a geometric structure, for example, projective structure, if you work with SLN, where N is even, but also more complicated geometric structures, which are all defined on compact fiber bundles over S. And it's actually quite hard in individual cases to determine what the fiber is. So as I said, I mean, I don't want to go into detail, but there's further work by Baraglia, Collier, Toulouse, Tolosan, Alessandrini and Collier, Alessandrini, Davallo and Lee, where partly use actually Higgs bundle techniques to say precisely what the fiber bundle is. Okay, so what is the second question which I was interested in, and this is what I want to tell you a bit more about today, is so we have this Hitchin component, we have these spaces of maximal representations which are defined for very different classes of groups. So one is defined for split real groups, the other is defined for Lie groups of emission type. And I want to, so the proofs of certain properties, for example, discreteness and faithfulness, use very different techniques, but the statements all are very similar. And so one question I wanted to understand, and this is the question I want to address a bit today, is what is the common underlying structure for these Hitchin components and for these space of maximal representations to exist? And related to this, the question, are these all examples of higher Teichmüller spaces we have, or could there be more? And for this, one of the key inputs or key observations is actually the theorem of Fock and Goncharov, who took a completely different approach. We're starting with working with surfaces which are not closed, but in the end, in their work showed that Hitchin representations can be characterized as some kind of positive representations. And at this point, I don't tell you what positive representation is, but this is one of the things I want to define in the talk. And so basically what I now want to try to explain is that positive representations, where I have to tell you what positivity here really mean, give examples of higher Teichmüller spaces, and this positivity really gives a common underlying structure to Hitchin components and to maximal representations. So perhaps before I set out to this, let me just stress for a moment again certain differences. So the way the Hitchin component was defined, it was defined essentially as clearly one connected component. And I mean, the first interesting result we saw is that it's homeomorphic to a vector space. So the space of maximal representations is defined by a characteristic number, coming from a Chern class, first Chern class of a certain bundle you associate to your representation. And it's defined by the maximality of this number. Since this is I mean, you can think of this number as a continuous but discrete valued function on the representation variety, it's clear that maximal representations form union of connected components, but in general, they are more than one. And the other thing is that they also usually are not, these components are not homomorphic to a vector space. And in fact, they have more complicated topology, and all the information again, and I'm not going to talk about this in detail, we have about the topology of this connected component. Most of this information, again, you get by using methods from the theory of Higgs bundles, so not by coming from studying geometric properties of individual representations in these spaces. Okay, so these are very different, but what I want to explain to you now is that from a certain perspective, these are really two animals in the same family. So to do this, I want to tell you what is positivity. And I want to first start by recalling or explaining what is the notion of positivity, which plays a role in this theorem of Fock and Gontcharov. So this is in this situation where we have a split Riemann group. So this is in the situation where the Hitchin components are defined. And if you look at a split Riemann group and you look at its Borel subgroup, so minimal parabolic subgroup, and then its unipotent radical, this gives you a maximal unipotent subgroup U of G. Then Lustig defined semigroup in this unipotent group, which he called the positive semigroup, and which generalizes to all split Riemann groups the following example from SLNR. So if you take the Lie group SLNR or PSLNR, for me it's easier to write SLNR, and then I can just write matrices and don't have to worry about quotients. Then the maximal unipotent subgroup is just the standard unipotent subgroup, upper triangular with ones on the diagonal. And this positive semigroup is the one which was defined much before Lustig defined that, where you look at a matrix, this unipotent matrix, and you put it in your positive semigroup if every possibly non-zero minor is actually positive. So of course it's unipotent. So if you take a minor where everything is zero, right? The minor is zero, but any minor which has a chance of being non-zero, you require it to be positive. This defines a semigroup in this group U. And when you do when you want to do it for split Riemann group, you have to, I mean, you can in the end also define it synthetically, but the way it's constructed is more by really constructing the semigroup by looking at root spaces and really writing down a parameterization of this semigroup. So I don't want to discuss that, but so you can think of this example for SLNR. If you never saw the construction for a general split Riemann group, and just remember for any split Riemann group, we have a similar semigroup in the maximal unipotent subgroup. And so now what I want to explain is that this such a semigroup gives rise to a notion of positivity for n tuples in the flag variety. And so for this, I will again just explain it for SLNR. So for SLNR, the flag variety is just a classical flag variety of flags of vector spaces. So a flag is a family of vector spaces, Fi, where Fi is contained in Fi plus 1, and the dimension of Fi is I. And if I give you a basis of R to the n, there are two standard flags you can associate to it. So the first, let's call it F0, where F0, the ith subspace in the flag, is just a span of the first I eigenvectors, and F infinity, where the ith flag ith subspace in the flag is just the span of the last I eigenvectors. And these two flags, these two standard flags, have the property that they are transverse, meaning that when you take the ith subspace of one flag and the n minus ith subspace of the other flag, you require them to have zero intersection. So now there is a basic fact about flags, and I mean this basic linear algebra for SLN. So if you give me a flag which is transverse to F0, then I can write it as the image of this other standard flag F infinity by an element in the unipotent, in this maximal unipotent subgroup. So this basically just follows by, I mean, taking the subspaces and writing when the stabilizer. Perhaps let me point out this one thing. The stabilizer of this standard flag is, of course, this standard unipotent subgroup where we have one on the diagonal and entries just above the diagonal. So now this tells me that if I take a flag which is transverse to F0, and I remember that I have F infinity at my hand, every element of U gives me a new flag. And now instead of just taking all elements in U, I have my positive semigroup, and I can look at flags which are the image of elements U, which are in this positive semigroup. And this you can now use to define what is a positive triple, or more generally a positive n-tuple. And so if you have an n+2 tuple of flags, F0, F1, up to F infinity, you say it is positive if every Fi is the image of Ui times Fi plus 1 with Ui in the positive semigroup. So if you just have a 3-tuple, you just require that your flag F is the image of F infinity by an element in this positive semigroup. So here's an example for SL3. So if I want to give you a flag in SL3, I have in R3, I have to give you a line and a two-plane. And if I look at this projectively, I give you a point in projective space and a line through this point. This is a flag. I can think of F0 as being one flag. If F infinity is transverse, I have the point which is not on the line and the line which intersects outside of this point. And then a third flag is actually forms a positive triple with F0 and F infinity if and only if I have this kind of configuration. So, which means that if I look at the triangle which is spanned by the three lines, so the 3 points in projective space, this is actually inscribed in the big triangle formed by the lines. So now if I have this notion of positivity for triples in flag varieties, I can use that to define what a positive representation is. So let's start with the representation of the fundamental group of my surface into my split real Lie group G. So for example, SLN. Then we say that it's positive if we find a map between boundaries, so between the boundary of this fundamental group of the surface, which we can identify if we pick a hyperbolic structure on the surface, we can identify this with RP1, with the boundary of the hyperbolic 2 space. And I want this map which maps this boundary of the group into my flag variety F in a way that it's equivariant with respect to my representation, and so that it sends positively oriented n-tuples in the boundary of my group. So in RP1, so I can just think of the positive orientation on the circle into positive n-tuples in my flag variety. So if you make this definition, you might wonder, okay, so I have to check this for all n. Actually, the way it works is that if your surface is closed, it's enough to check it for 3 tuples. And if you would deal with a surface which is not closed, but might have punctures, you should actually work with 4 tuples instead of 3 tuples. But so this now gives us what this notion of positive representations, and then you can I just rephrase again the theorem of Fock and Goncharov, which says a representation from the fundamental group of the surface into a split Rayleigh group lies in the Hitchin component if and only if this rho is positive in this sense. And I would like to just mention shortly at this point that actually their proof uses not just the definition of the Hitchin component, but it also uses some other properties Nigel proves in this paper, namely, for example, that every representation in the Hitchin component is in fact irreducible. So this is one thing which enters in this proof of the theorem by Fock and Goncharov. Okay, so now this gives us a bit of background and lets us understand how representations in the Hitchin component can be characterized in terms of total positivity in split Rayleigh groups. So now what I want to explain a bit is how you can generalize this notion of total positivity. So basically this is something which Olivier Guichard and me, many years ago, we started wondering, I mean, is there a generalization of this total positivity which includes some of this picture we see for maximal representations? And yeah, so let me describe this, and let me describe it in terms of looking first at what are the key properties which play a role in Lustig total positivity in order to get this set of positive representations, and also in order to prove some of its properties. And what is really a key property is that this positive semigroup Lustig defines has this property that, I mean, it allows you to define these positive triples, but this set of positive triples, so we had this positive triples where F, we have the standard flag, F0, then a flag F and F infinity, right? So these were the positive triples which are basically precisely parameterized by this positive semigroup. And these positive triples are a subset of the set of transverse triples, but it's not just a subset, but it's actually a connected component. And so this is one of the key features in the positivity. And so you can ask yourself, okay, so can we find other situations for other Lie groups where we find a similar situation? So basically what we want to look at, so G is now not a split Rayleigh group, but you start with any semi-simple Lie group. Then you start with any generalized flag variety. So any generalized flag variety, it's a homogeneous space G modulo a parabolic subgroup. And I write here the theta because these parabolic subgroups are determined by a subset theta of the set of simple roots. And then, I mean, we saw in the total positive case that we don't really look at the parabolic subgroup, but we really looked at its unipotent radical. So we take this, we look at the generalized flag variety, we have this parabolic subgroup, and then we have its unipotent radical. And basically, what do we want to try to find? We want to try to find in this unipotent radical, we want to find some semigroup, which we call the positive semigroup, which has the property that if we define positive triples in the same way as we did before, the set of positive triples in the set of transverse triples is a connected component. So for this, so you look at, again, I mean, pick two standard generalized flags, F0 and F infinity, and you look at the set of triples F0, U times F infinity, where U is in a semigroup in this unipotent radical. And you don't want, so you want to have this property that you find a semigroup, but this semigroup has this property that if you take this set and you look at it as a subset of the set of triples of flags where F is transverse to both F0 and F infinity, you get a connected component. So a priori, this is perhaps a bit complicated to understand. And it's actually not the way we in the end define the semigroup, but this is really the geometric key feature that you would like to have. And so having that, so you can give a classification of Lie groups where this happens. But before I want to give that, I want to give an example. And this is really an example which plays a role in the context of maximal representation. So if you take the group sp2nr, so this is a Lie group of Hermitian type. It's also a split Lie group, so it also appears in total positivity. But for total positivity, we would look at the full flag variety. And now we can look at a different flag variety, namely at the partial flag variety, where we just look at the space of Lagrangians. And so if I, again, fix a basis or a symplectic basis EI, Fi, then I have my two standard Lagrangians, which are in general position, can take the span of the first n basis vectors and the span of the last n basis vectors. And then if I look at the unipotent radical of this parabolic subgroup, this is an upper triangular unipotent group, block triangular group. So I have identity matrices on the diagonal, and I have one matrix in the upper right corner, which is the symmetric matrix, and the positive semigroup we look at is the positive semigroup where this matrix here is not just symmetric, but it's actually positive definite. And then if you look at, I mean, let me write this here below. So if you have three flags F and you have some U F infinity, then so you have U is in this positive semigroup in this situation if and only if the Maslov index, which is an invariant of three Lagrangians, of these three Lagrangians, is actually equal to n in this case. So there's another way to characterize that. But here you have a very simple situation because the unipotent radical is just, you can identify it with symmetric n by n matrices, and you have a positive semigroup given by the positive definite matrices. But this example is really, and this is one thing which we understood with Mark Burger and Alessandro Iotti before trying to generalize positivity, is that, I mean, you have this structure, which is very similar to the structure of low-stake total positivity, and you can characterize maximal representations as those representations where you have a row equivariant boundary maps, which sends positive-oriented triples to triples of maximal Maslov index. So this was an example. So now let's look at when we classify this more general situation for any semi-simple Lie group. Let's look at the simple Lie groups, because the semi-simple are just product of simple Lie groups, and you just get product structures of these things. So when you start to classify this, you see that we don't just have the two families, which are split Lie groups and Hermitian groups, but you actually get two more families. So there are four families of simple Lie groups which admit a positive structure. So the first one, which we saw, split Lie forms, where the flag variety you look at is the full flag variety. So the parabolic is actually the Borel subgroup. The second is Hermitian Lie groups, which are of tube type. And there, the parabolic subgroup you look at is maximal parabolic subgroup, and the corresponding flag variety would be the Shilov boundary of your Hermitian symmetric space. And these really correspond to these maximal representations. And then there are two more families. One, groups which are locally isomorphic to SOPQ, where 2 is smaller equal than P and less than Q. And the parabolic and flag variety you look at here is neither neither the minimal parabolic nor maximal parabolic. It's an intermediate one. So it's the flag variety of isotropic flags, where you have spaces of dimension 1 up to p-1 and not up to p. And then there's an exceptional family. So you have one for each exceptional group F4, E6, E7, E8. There's a special real form, and again, the parabolic subgroup is an intermediate parabolic subgroup. So when you look at this list, I want to make one comment about it. So the split regroups of type Bn, Cn, and F4 appear twice. So they appear once, they appear once as a split reform. But then if you are of type Cn, you are Hermitian. So this is the symplectic group, which appears as a split reform and as a Hermitian form of 2 type. If you are of type Bn, this is SONN+1. It appears as a split reform and as an element in this family. And the split reform of F4 appears once here and once here. So for these groups, you have 2 different positive structures, and there's some connection between and relation between the positive semigroups, which tells you that somehow in this case, for example, for Cn, tells you that the Hitchin component actually is one component of the space of maximal representations for the symplectic group. So let me make one other comment. So in order to get this classification, you do not really start with this definition I gave here, with the geometric definition. So you start more with a more algebraic way of constructing this semigroup, which allows you to read off the root system of your Lie group, whether you have a positive structure or not. And there are many properties of Lustig total positivity which extends, but there are also many questions about totally positive matrices, or in particular non-negative, the non-negative semigroup, so the closure of this positive semigroup, which we don't know yet how to describe them. For example, the interesting combinatorics of it for this generalization of Lustig total positivity, where we only know the answer for Lustig total positivity. So there are a lot of open questions about these positive structures in Lie groups, just in the Lie group, not taking into account any representation. But today I want to take into account the representation, and so let's look at this set of positive representations. So I don't want, how is it defined? So similar to what I explained for Lustig total positivity, once we have this positive semigroup, we can define the notion of positive n-tuples on our generalized flag variety. And so if we have a representation of the fundamental group of our surface into our Lie group G, which admits a positive structure, we can define the set of positive representations in the same way as how we did it before. So let me just go back to that slide. So you just take precisely the same definition as here. So you have a representation. So now G is not necessarily split, but G is a group which admits a positive structure. And then you call a representation positive if there exists a row equivalent map from the boundary of your surface group into your partial flag variety, which with respect to which you define the positive structure, sending positive oriented n-tuples to positive n-tuples in this generalized flag variety. Okay, so if we have that, so this tells us that we have this set of positive representations in the representation variety, in the set of all representations from the fundamental group of S into G. And so when we classified this groups admitting a positive structure, we made this conjecture that all these positive representations actually give you connected components, which consist entirely of discrete and faithful representations. And so we now can prove this in full generality. And so this, if you look at this set of positive representation, it is a union of connected components consisting entirely of discrete and faithful representations. So it gives you other examples of higher Teichmüller spaces. And the story is a bit, so there are three papers which I mentioned here. So in the first one with Olivier Guichard and François Labourie, what we prove is first that any positive representation is discrete and faithful. It's actually even more, it's what's called an Anosov representation. And using this property, you can show that it gives you the set of positive representations, gives you an open set of the representation variety. And then we show here not the closeness, but we just show it's closed among the representations which are not contained in a parabolic subgroup. And if you combine this with some work of Bradlow, Collier, Garcia Prada, Goten, and Oliveira, you already get certain connected components in the space of positive representations, which consist entirely of discrete and faithful representations. So then there's work of Beira and Pozzetti where they looked only at the group SOPQ and proved fine properties of elements in this group, in particular a generalization of the color lemma from hyperbolic geometry in this setting of positive representation to SOPQ to actually show that positive representations in SOPQ are closed. And in very recent work, which is, should appear very soon on the archive with, Beira, Pozzetti, Guichard, Labourie, and myself, we actually prove a color lemma for theta positive representations. So for these positive representations in complete generality, and using this, you prove also in complete generality that the set of positive representations is closed. And here I would like to just make one note. So far I always assumed that the surface is closed of genus bigger or equal than 2. So the I want to make one comment here. The proof of closeness also works actually for any surface S, so not necessarily closed. It can have punctures, and it also doesn't necessarily have to be of finite type. So you need negative Euler characteristic, but you don't need to be of finite type. And so I just want to mention here because it opens up a bit the going in a direction where you could study these set of positive representation for surfaces and these higher Teichmüller space for surfaces which are not of finite type, but which have infinite genus or infinite number of punctures. So now I would like to come back to Higgs bundles. So I talked now a lot about other structures on the Lie group and structures on the Lie algebra, and then representations, how you apply this to get this nice class of representations. So if G admits this positive structure, the way you actually construct this positive semigroup, you also show and see that this G, if it admits a positive structure, it admits a split real Lie group. So a split real Lie group, which is embedded as a subgroup, which is associated to this subset of the set of simple roots theta. And it also, this split real Lie group, again, now, of course, contains a special SL2, namely its principal SL2. And you get these special SL2 coming from the principal SL2 of the split real Lie group embedded into G, which we call theta principal SL2. And so there's, if you look at the complexification of this SL2 and look at this SL2 in the complex, in the complex Lie algebra, it's an example of what when Bradlow, Collier, Garcia, Prada, Goten, and Oliveira call a magical SL2. And they, and I hope or assume that Steve will probably talk a bit more about that, really extend Hitchin's original ideas from the paper, in the Lie groups and Teichmüller space paper, to these magical SL2s. And with these techniques give a parameterization of what we all believe to be precisely the set of positive representations, but what is for sure a subset of the set of positive representations. So it's not yet in particular for the exceptional case proven that it's actually the same set. But the way I would like to look at it, so I'm convinced it will really parameterize the full set of positive representations. So I want to look at this, and this brings me to a couple of open questions I want to address at the end of this talk. This parameterization, you should think of it as, in some sense, having in this generalized, in this general setting, something like the Hitchin section, but we have the section without really having the corresponding Hitchin map. And so this is one of the open questions I would like to mention, and it's actually a question I'm quite interested in currently, is there an appropriate Hitchin map for these three other families of positive structures? So when you're not split real group, but either Hermitian type or SOPQ or this exceptional group, such that which allows you to think of this parameterization as some kind of section to this map. And so I would like to just mention where there are some steps for this, for some at least Hermitian groups of tube type. So if you think of, the Hitchin map to some extent really comes from looking at invariant polynomials on the Lie algebra. And there is a way to think of these Lie groups of Hermitian type, at least the classical ones, not the exceptional one, but the classical ones, as some kind of Lie groups of type SP2 or SL2 over some non-commutative rings or non-commutative algebras. And the, in some sense, motivation to think about them in this way really comes from this positive structure you see, and some of the structure you see in this positivity for Lie groups of Hermitian type. And if you realize, for example, the symplectic group, so if you realize the symplectic group SP2 and either C or R, you can think of this as SL2, or it's better to think of it as a symplectic group, so SP2 over the ring of matrices with transposition. And if you do that, so you get the first steps in the direction of having some appropriate generalizations of invariant polynomials. So you can define on these groups a trace which has values in this non-commutative algebra, and also determinant function which have values in this non-commutative algebra. The problem is these are not invariant functions in the classical sense, so they are not invariant by the action of conjugation, but they satisfy an appropriate generalization of the Cayley-Hamilton theorem. And actually there's a lot of interesting structure to do that. So you can, for example, use that to define quantizations of these groups similar to the quantum SL2 for SL2 over field. And so what I believe, but I can't make it precise really, and give a really good precise way of defining this map, but that you can like to see that you can use this a value trace and determinant function and corresponding determinant line bundle to actually write down non-commutative version of the Hitchin map in this situation. So this was one question, open question I wanted to address. Here are two others, which also partly resonate a lot with work of Nigel. So the second one, and again, this is the second one. This is something where I really think people who have much more experience with Higgs bundles should finish the proof. So we know that these positive representations really account for additional connected components in the representation variety for real groups. And I think we all believe that these are all, these really explain this phenomenon that we have for a real Lie group more connected components than those given by characteristic numbers. But we don't have a proof of that. Third open question I would like to mention is, there's some very interesting work of Nigel's for the Hitchin component to go to more thinking of the Hitchin component in infinite dimensional Lie groups. And here for this positive, other positive representation, a very interesting family are these groups SOP infinity, because these are infinite dimensional Lie groups, but of finite rank. So there's a lot of nicer structure on them. And as last question, I want to come back to one question or problem Nigel raises in his paper on Lie groups and Teichmüller space. So he somehow says, oh, it would be nice to have this geometric, to know that these parameterized geometric objects, because then we get a natural action of the mapping class group. And then we can look at the quotient of these of the Hitchin component by the mapping class group, and perhaps also its compactifications. And so we know now that we have a nice action of the mapping class group. We can look at the quotient, but the quotient is infinite volume. And so it's very different from the quotient of Teichmüller space, where the modular space has finite volume and also very nice compactifications. And I think it's a very interesting question to understand whether there's something bigger than the mapping class group which acts on these components of positive representation. So first example would be to really look at the Hitchin component, which is not defined by looking at the topology of the surface or not as a mapping class group, but really uses the symplectic structure of the representation variety. So where you look at the bigger group of symplectomorphism and try to find one which acts properly but with finite volume quotient. And this is the last open question, and I hope that, Nigel, you find some of them interesting, or interesting to see perhaps at some point answers about them. And with this, I would like to stop. Thank you.
Thank you, Anna. I realize that it's past 11 p.m. in Leipzig now, but so what is this non-commutative spectral covering that you just mentioned?
Well, it's not, I don't know, okay, I don't say it's a spectral covering, but so the thing is, I think this is actually something which I don't know if there's, if you're thinking of something like a non-commutative spectral curve where that such a thing exists, but what is quite curious is that, so you can, if you start, so you can think of this symplectic group as this somehow symplectic groups of rank 1 over this over the ring of matrices. And when you do this, there's a very natural, if you take the standard trace of a matrix just as the sum of the diagonal entries, this gives you a trace into this non-commutative algebra, so into the ring here, into the ring of matrices, which a priori looks like a very dumb thing to do. But then you realize that there's actually a very nice, it appears in very nice situations. So you can write down this generalization of Cayley-Hamilton theorem where your involution appears, this, so taking the transpose in this situation, the involution appears some cases, but you get out of this, for example, trace identities, which generalize the SL2 trace identities, where, you get the SL2 situation when you take the trivial involution, but for non-trivial involution, you get something different. And So in this somehow in this flavor, I think there should also be. So you should think of invariant polynomials, not in terms of invariant polynomials, but invariant functions, as thinking of this group as an object, really like an SL2 theory of over this non-commutative ring. And I mean, yeah, so I think it's probably too much to discuss all this now, but I would be very happy to discuss this with you.
So the image of the Hitchin map are not just multi-sections, but multi-sections with matrix value multi-sections.
Well, I think what you should really have is, I mean, one thing is that you already, I mean, if you take the determinant line, I mean, if you take the determinant bundle, I mean, you have you start with a, if you start with an A bundle and you A squared bundle and you take its determinant line bundle, this is not a line bundle, right? It's an A line bundle. So one piece of the information you get is a bundle over the surface, and then you get from the trace and the determinant itself, you get a section. You would get a holomorphic section of this bundle. Right?
Okay, thank you. Other questions? Yes.
Well, thanks. I did find it a very interesting talk. Could you say a bit more about what your model for SOP infinity is?
What the model for SOP infinity is? So, I mean, SOP infinity, so basically you take, I mean, you can think of it as you take a Hilbert space, which has with a quadratic form on it, where it has, I mean, the maximal dimension of a positive of a subspace on which it restricts to a positive definite form is P. And then you can think of, I mean, you can build the whole theory of, you can build this metric space. I mean, this is something people did. You can build this metric space for it. For example, it's the space of P-planes. I mean, positive P-planes in this space. You can look at the boundary. You have this, I mean, the generalized flag variety would be the flag space of, I mean, isotropic subspaces of dimension 1, dimension 2, up to dimension P or P-1 for this positivity. So the interesting thing is because you have, I mean, among these infinite dimensional Lie groups, these are very special because these are finite rank. So a lot of the constructions you do classically for finite dimensional Lie groups still work, because you still, whenever you have something which happens to appear in a flat subspace or something, this is actually a finite dimension.
Yeah, hi. Is there an answer to your question before here that's still on the screen for SL2R plus SL2R, like the rotated one of the vector space?
So sorry for
plus SL2R. So I think it's like
yes, I mean okay.
Is there such a bigger group? No.
Yes. So for SA, I mean, okay. So the only case where I can prove that, so I have, I mean, I have something which I believe should give you something like that. The only case where I can prove that is SL2 cross SL2, or SL2 to, I mean, copies of SL2. And what the construction gives for copies of SL2, it naturally gives not the mapping class group, but the product of the mapping class group with itself. So if you have n copies of SL2, you would construct a subgroup of the group of symplectomorphisms, which is really a product of mapping class groups. And of course, this case, it's not surprising, because we know we look at positive representation in SL2 cross SL2, we just get Teichmüller space cross Teichmüller space. And I mean, we have the natural action of the mapping class group on it would be the diagonal action of the mapping class group. But here you can construct it in such a way that you really have the product, the mapping class group acting on one copy and the mapping class group acting on the other, and you have the product of the two mapping class group actions on it.
Other questions? Danke vielmals. Ich habe sehr schön. Wiedersehen.